One of the defining features of biological aging is a decline in the body's capacity to regenerate, manifested as slower wound healing, hair thinning, reduced muscle recovery, and weaker immune responses. These symptoms are often attributed to stem cell exhaustion, the diminished ability of tissue-resident stem cells to proliferate and differentiate in response to damage. But what if stem cell aging is not simply the result of an intrinsic, time-driven depletion, but a reflection of decades-long nutritional insufficiency? Mounting evidence supports the idea that stem cell function is highly responsive to nutritional status, particularly to the availability of growth factors such as IGF-1 and the micronutrients that regulate them: protein, zinc, and selenium. From this view, what appears to be stem cell failure with age is in many cases the biological consequence of unmet metabolic and anabolic needs. Regeneration slows not because the blueprint has worn out, but because the construction crew has run out of supplies. Stem cells are housed in specialized microenvironments called niches, which tightly regulate their activity through a complex interplay of biochemical signals. One of the key stimulatory factors in this environment is insulin-like growth factor 1, IGF-1, a hormone that promotes cell proliferation, survival, and differentiation. IGF-1 levels are known to decline with age, and this reduction is strongly associated with loss of muscle mass, impaired tissue repair, and slower recovery from illness or injury. But crucially, IGF-1 synthesis is highly dependent on dietary protein intake, particularly the availability of essential amino acids like leucine, which activate mTOR signaling, an upstream regulator of growth factor production. When dietary protein is insufficient, either due to calorie restriction, imbalanced diets, or poor digestion, IGF-1 production drops and stem cell activity is suppressed accordingly. This does not reflect a permanent decline in regenerative capacity. It is a conditional response to perceived nutrient scarcity. Zinc and selenium also play central roles in maintaining stem cell health. Zinc is required for the activity of over 300 enzymes and is essential for DNA synthesis, cell division, and growth factor signaling. It is particularly concentrated in proliferative tissues such as the thymus, bone marrow, and intestinal lining, all regions with high stem cell turnover. Chronic zinc deficiency impairs immune regeneration, reduces hair follicle cycling, and delays epithelial repair, all symptoms commonly interpreted as signs of aging. Selenium, a critical component of antioxidant enzymes like glutathione peroxidase, protects the stem cell niche from oxidative stress. Without adequate selenium, the stem cell environment becomes hostile to renewal, favoring senescence and cell cycle arrest. Yet both zinc and selenium deficiencies are surprisingly common, particularly among the elderly, vegans, and those with gastrointestinal absorption issues. The key insight is that stem cells do not simply burn out with time. Rather, their quiescence is often a programmed response to environmental signals, chief among them, nutritional status. The body interprets chronic undernourishment as a signal of hardship or scarcity, and in turn, downregulates growth, regeneration, and repair to conserve energy and resources. This survival-based shift is logical. When protein, zinc, and selenium are scarce, it is metabolically safer to pause tissue renewal than to proceed and risk incomplete or faulty regeneration. But when nutrition is restored, particularly with sufficient quality protein and trace minerals, stem cell activity can be reawakened. This has been observed in studies where refeeding after protein energy malnutrition restores IGF-1 levels and accelerates wound healing, hair regrowth, and immune responsiveness even in older individuals. Clinical interventions support this reactivation model. Protein supplementation in older adults has been shown to improve muscle protein synthesis, bone healing, and post-surgical recovery. Zinc repletion improves immune resilience and skin regeneration. And selenium supplementation reduces oxidative stress in regenerative tissues and improves outcomes in thyroid and immune-related disorders. These benefits are not achieved by pushing stem cells artificially. They are achieved by giving them the nutritional conditions to do what they were always capable of doing: repair, rebuild, and renew. It's also worth noting that calorie restriction, often touted for its anti-aging effects, must be viewed in the right context. While modest restriction may reduce oxidative stress, excessive or prolonged restriction without adequate protein and micronutrient density can suppress IGF-1 and reduce regenerative capacity. This trade-off may protect against cancer in some models, but it can also accelerate sarcopenia, cognitive fatigue, and immune suppression. The key is not to reduce nutrients, but to optimize their quality and bioavailability, fueling the body's regenerative machinery rather than starving it into dormancy. In this context, stem cell aging is better framed as a nutrient-sensitive dormancy rather than irreversible depletion. The potential for repair and renewal remains embedded in our biology, but requires the right biochemical inputs to be realized. Nutritional interventions that prioritize protein quality, zinc sufficiency, and antioxidant support do not merely maintain existing function, they actively rejuvenate. This shifts the narrative of aging from inevitability to possibility. Our stem cells are not gone, they're waiting. And when fed properly, they still remember how to rebuild.